So we have a proton traveling with a velocity 9 to the power of 5 meter per second collide elastically with a second proton that is stationary. So because the second proton is stationary, so the initial velocity for the second proton will be 0 meter per second. So after the collisions, the first proton moved with a speed of 4.5 to the power of 5 meter per second with an angle 60 degree from its original directions. Find the speed and the angle for the second proton after collisions. So we need to calculate what is the speed, what is v2 after collision for this second proton and also the angle, the direction. Okay, so we can see obviously this is a 2D collision whereby it involves x directions and also y directions. So in order to calculate the final speed of the second proton after collisions, we are going to follow these problem solving steps whereby first we need to break the velocity into x and y components and remember to put negative sign for any leftward and downwards direction that you already known in the question. Then second one, we are going to write the conservations of momentum for x and y separately. So first step, we are going to break all the velocity into its perpendicular component, x and y. So we consider before collision dulu. So we consider before collisions. So before collisions, the first proton is moving rightward. So the 9 to the power of 5 meter per second will be the initial velocity component, x. So the initial velocity for first proton y component will be 0. Okay, this proton doesn't have any component y. So for the second proton is initially stationary, so the ux will be 0. Same go for the initial velocity second proton along the y-axis also will be 0. Why? Because it is stationary, sebab dia tidak bergerak kan? Okay. Then we consider after collisions. Okay, after collisions, the first proton is moving with V1 at angle 60 degree. So we can break it down in, so this V1 I can break it into component X and also component Y. So I'm going to have X component will be 4.5 to the power of 5 cos 60 because the component x is adjacent to the angle. Then I have also the component y. So the component y for the velocity v1 will be 4.5 to the power of 5 sine 60. Okay, so I have break down v1 into its component x and also component y. And since go for v2, I can break it down into component x and also so I'm going to have v2x and v2y. Okay, but I didn't put a negative sign for v2y because the directions is unknown. I'm not very sure whether this final velocity for proton 2 is moving downward, so I just write it as v2y. Okay, so I have already break down the velocity into x and y component. Then now I can write the conservations of momentum for x and y separately in order to determine the speed and the angle of the second proton after collisions. Okay, so refer to the component that we already break down into x and y. Now we write the conservation of momentum for both components. So refer to the x component or x direction. So we apply the conservations of momentum. So the total momentum x before must equal to the total momentum x after. So refer to the diagram. This will be the component x for the proton before collisions, and after collisions, first proton are going to have velocity component x 4.5 to the power of 5 cos 60, and this is the velocity component x for the second proton. So I have the mass. I assume the mass of the proton is m because the question doesn't give the mass. So I just assume the mass of proton is m. So I have m multiplied the Initial velocity of first proton before collisions along the x-axis is 9 to the power of 5. Okay, plus with the momentum for the second proton before collisions. Because the second proton is initially stationary, the velocity is 0. So the momentum before collision for second proton will be 0. Okay, then equal to the momentum along the x component after collisions. So after collision, the first proton is moving along the x direction with velocity 4.5 to the power of 5 cos 60. So I'm going to have m multiplied 4.5 to the power of 5 cos 60 plus with the mass of the second proton, and this second proton is moving with a velocity v2x along the x component after collision, so v2x. Okay, I can cancel the common m on both sides of the equations. Then I solve this equation. You may pause the video to solve it. Then we will get v2x will be 6.75 to the power of 5 meter per second. Okay, so we already calculate the final velocity for the second proton along the x component, x directions. Then we do it for y component. Okay, we do it for the vertical component. So again, we are going to apply the conservations of momentum. So now the total momentum along the y component before collisions must equal to the total momentum along y component after collisions. Okay, so if we refer to the diagram, the first proton is moving rightwards before collisions. There is no component y, there is no velocity component y for the first proton and also the second proton. It means that the total momentum along the y axis before collision will be 0. Okay, so class you boleh nampak dengan. So you can see obviously sebelum pelanggaran, dua-dua proton ni tidak ada sebarang pergerakan sepanjang y-axis. Dia hanya bergerak secara horizontal. That's why momentum along y-axis before collision adalah kosong. How about after collision? After collision, you can see obviously first proton is moving at a speed of with a velocity of 4.5 to the power of 5 sin 60 along the y-axis. And also second proton is moving with a velocity v2y, which is unknown that we want to determine. So we have the momentum for the first proton after collision will be m multiplied the final velocity for the first proton along the y-axis is 4.5 to the power of 5 sin 60. Okay, plus with the mass of the second proton multiplied with the final velocity along the y-axis, the y component for second proton, which is v2y. So this v2y is what we are going to determine. So you may pause the video to solve for the v2y. So I rearrange the equation. So I'm going to have negative m v2y equal to m 4.5 to the power of 5 sin 60. So I can cancel the common m on the both sides of the equation. Then I'll solve for v2y. So I'll get my v2y will be negative 3.897 to the power of 5 meter per second. Okay, no worries with this negative. It's okay. So this negative telling you that yes, our second proton is moving downwards. So means that our drawing is correct lah. So this negative showing that the second proton is moving downwards, okay, in downwards direction along the y-axis, okay. So after we have get the component x and component y for the v2, then we can determine the magnitude of v2 lah. Okay. Then I can calculate the v2 using the theorem Pythagoras. I have v2x squared plus v2y squared square root. So I'm going to have 6.75 to the power of 5 squared plus with the y component is negative 3.897 to the power of 5 squared. So you may pause the video to calculate the magnitude of the final velocity for the second proton. So if you do it correctly, you should get 7.79 to the power of 5 meter per second. How about the angle, the direction? So the theta, the angle, the direction for the second proton after collisions can be determined using shift tangent v2y over v2x. So I have shift tangent negative 3.897 to the power of 5 over 6.75 to the power of 5. So I'll get the angle will be negative 30 degree. No worries with the negative telling us that the angle is below horizontal. So no worries with this negative, this negative telling us that the angle is below positive x. Okay, so we obtain our answer. The speed of the second proton after collisions will be 7.79 to the power of 5 meter per second at an angle 30 degree below positive x. Okay, so this will be our solution. Always bear in mind when we deal with collision 2D, first step we need to break all the velocity into each component x and component y. Then only we write the conservations of momentum for x component and y component separately. From that we can determine the missing velocity for an object. Okay.